Hey y'all, welcome back. This is lesson 4C. In this lesson, we'll be covering contrast for the generalized random complete block design. We will be talking about contrast for the treatment effect and contrast for treatment effects within a specific block. This is all going to be tied back into our reaction time example. So let's get started. Recall that in our reaction time example, we were looking at the influence of alcohol with a block effect of age. Within each block treatment combination, we had 4 individuals. So we have replication, which allows us to do the RGBCD design. In our last couple of lessons, we saw that we first test our interaction, which is seen right here, looking at our F and our p-value. We saw that our interaction was significant. So our next step was to look at our interaction plot, where we saw that this was codirectional. And so this gives us the ability to go look at, or allows us to go look at the tests for treatments, and we saw that our test for treatments was significant based on this large F and p-value. Now, just like in the complete random design and the random complete block design, we had follow-up or post-analyses such as Tukey's and Fisher's, which was the multiple comparisons, and we had contrasts. In this video, I'm going to focus more on the contrast, but you can do Tukey's, and I'll show you how to do that in these software videos. All right. So let's talk about doing contrast for a specific treatment effect. We've seen this notation before, where our population contrast is the sum of our contrast coefficient CI times our mu, or you can look at it as our alpha. Again, we have a constraint where our contrast coefficients have to sum to 1. Our estimate for our contrast, L hat, is our coefficient times the treatment mean. Okay? Our F treatment effect, we're looking at whether the contrast, population contrast is equal to 0 or not. We have our sums of squared. We will have our F statistic. Now I'm going over this pretty quickly because we've seen this before. Now, let's use this within our reaction time example. So maybe a researcher suspects that the reaction time depends linearly on the alcohol level. This means that the treatment effect change when increasing the alcohol level from 0 to 1 is the same as the treatment effect change when increasing the alcohol level from 1 to 2. Okay, so I forgot to put the main effects plot, but here's our main effects plot from our previous lesson. What this is really asking, this specific question, is this slope different than this slope? This slope different than this slope? Okay, and that's how we're getting our hypotheses right here. Treatment 1 minus treatment 0, is that the same as treatment 2 minus treatment 1? Our alternative is that they're not equal. An equivalent form, more in terms of the contrasts, would be minus alpha 0 plus 2 alpha. This should be a 1. Make sure I do my math right. 1, 1, and that's also a 1. Okay, so let me just talk a little bit about how we got here and what our contrast coefficients would be for this particular example. So we're going to start at this hypothesis. So we're going to have alpha 1 minus alpha 0, alpha 2 minus alpha 1. And how we're going to get our L is by bringing either this side over here, or vice versa, you could bring that side, which we'll talk about in a second. And so when you do that, you will see that we're going to have a minus alpha 0 plus 2 alpha 1 minus alpha 2. And in this one, our contrast coefficient for the 0 level, or 0%, not 0%, 0 ounce of alcohol, is minus 1. C1 is 2, and C2 is minus 1. Notice that they sum up to 1. Another way you could have done this, let me find another pencil, is instead of bringing it over here, you could bring these terms to this side, which would result in an L equaling to alpha naught minus 2 alpha 1 plus alpha 2, where our C naught then would be 1, C1 would be minus 2, and C2 is 1. Okay, so our contrast coefficients, and these are the numbers that you will be plugging into JUMP or R, are coming from our hypotheses when we move everything to one side. And so now our L is equal to this or this. Okay, really what that would change is if you're looking at the T statistic, whether it's going to be positive or negative. But I account for that in your Canvas homework, or at least I try to remember to. Cool. So here's how you would estimate it. Here's your sums of squares. Here's your F statistic. And then we get our p-value from software. So this is what you would see in JUMP. And then with this conclusion, with a p-value less than 0.0001, this implies that the change in reaction time when increasing the alcohol level from 0 ounce to 1 ounce differs from the change in reaction time when increasing the alcohol level from 1 ounce to 2 ounce. And that makes sense, especially if we go back and we look at our main effects plot. This slope and this slope do look different. Now again, remember the caveat. When we talk about just the test of treatment, because again, this was just looking at the treatment effect. Just because the treatment effect contrast in this specific case was significant, it does not mean that within the blocks we will be significant. And so that leads us to this next test, where we're going to look at the treatment effect within a block contrast. Okay, so maybe in group 1, this blue line, the means don't differ, but in the red and green line, the treatment means do differ. And so this is going to allow us to really look at the interaction, the treatment effect within block. Okay. So here's some notation and formulas. I don't expect you to know this. Our users, I'm giving you a heads up right now, please go watch the video for this. There wasn't a simple function or package that allowed us to do it as simply as JUMP. So I'm going to have you end up calculating these L hats and stuff. But I just want to give you a forewarning. Go watch the video now. And if you have questions, try to ask them early in the week. Sorry for that plug, none are users. But back to what we were doing. So here's the equations. Here's our estimated contrast. Now notice that here, this J, we're going to be looking at a specific block. So let's go look at our F test again. Our hypotheses are going to be looking at the population contrast for a specific block. Here's our sums of squares contrast. Here's the F test, but let's look at an example. This is the exact same example that we were just looking at before, but now we're interested in just the third age group. So in the first example, we were looking at the difference between the effects of the slope on the main effect plot. Now what we're looking at is the difference in the slopes with this green line. So this one, does this differ from this? Only within this third block. Okay? Our hypotheses are the same, but now we have a subscript, this 3, which is going to represent the block 3. Okay? And so again, we're going to take these values and we're going to move them to one side or the other, depends on which way you do it. And we're going to get this hypothesis where our L is minus mu 0, 3. So this is treatment 0 in block 3 plus 2 times the mu of treatment 1 in block 3 minus the mu of treatment 2 in block 3. Again, this is where our contrast coefficient, so minus, plus 2, minus. And again, in software, we'll talk more about it watching the respective videos. We then can do our estimate, sums of squares, f-stat, and then we get a p-value. Notice that in this example, our p-value is higher and our F ratio is smaller. Okay? That's just kind of going back to the whole thing of just doing the treatment effects doesn't explain everything that's going within individual blocks. Again, so here what we can conclude is that this means that within the third group, the change in reaction time when increasing from 0 to 1 differs from when we increase from 1 to 2. That's the end of these notes. Go watch your respective R or JUMP software videos and start your homework. I hope you have an amazing day, week, and weekend, and see you in the next lesson.